Did you know that the universe has a speed limit? And no matter how long or how hard anyone or anything has ever tried, no one has ever passed it. Not cars, not people, not sound or information, not even rocket ships. This speed happens to be 186,000 miles per second, the speed of light, known as c. This limit is incredibly fast, like 7.5 times around the Earth in 1 second fast. Still, you might think it's odd that the universe has a speed limit, and perhaps you might think that you're clever enough to break it. Well, let's first take a closer look at where this limit comes from. So what is speed, or velocity anyway? Well, speed is defined as the ratio of an object's change in space over the change in time. We all have a good sense of what space is, and we often use Cartesian coordinates to describe it, although you will see later in this video that there is much more to it. But what is time? Well, we can think of time as the potential for change. Whenever we are measuring the speed of an object, we are actually measuring its change in space with respect to the change of something else. That something else can be the rotation of the Earth around the sun, or the changing hand on a clock. And we use these other standard observations to define and quantify the passage of time. So the words faster and slower are only defined in relation to these clocks. Now, what if I were to tell you that I can put my pen on this paper and move it up or down, and yet nothing will be drawn? You'd think I'm crazy, right? Well, take a look at this. I just did it, as you can see. I moved my pen, but also the paper. So while the pen was in motion with respect to you, it was not with respect to the paper. Therefore, no picture. Now if I do keep the paper stationary, then I can draw. Voila! I can draw straight lines, fast or slow. I can also draw curves. So all of these motions you see are relative to the paper and you. The curved lines were drawn with an acceleration. Their velocity was changing direction. But in the special case where the motions follow a constant velocity, a straight line, we refer to that as special relativity. Einstein, in 1905, published a revolutionizing paper about this, and it changes everything we know about space, time, and even matter. His work is all about how different reference frames moving in constant velocity relate to each other. So let's say you're in a car and you're driving your sister to school. We'll call you guys reference frame A. And your dad is standing by the side of the road watching you guys off. We'll call him B for bystander. So he sees you guys driving away at, let's say, 50 miles per hour. But from your perspective, when you and your sister look at each other, you're not moving relative to one another or the car. Now your sister decides to throw a baseball in front of the car, which moves away from you two at 80 miles per hour. To your dad, however, this ball was already initially moving 50 miles per hour in the car. Plus another 80 miles per hour, it's really moving away from him at 130 miles per hour. By this same logic, if the passenger shot a laser beam forward, it should travel away from her and the car at the speed of light, 186,000 miles per second, which is also 670 million miles per hour. And to the bystander, it would be the speed of the car plus 670 million, which yields this larger speed of the laser beam. This all makes sense. Well, there's one problem. Maxwell discovered some relationships between the speed of light, electricity, and magnetism in this equation. But whose speed of light are we supposed to use? Yours when you're driving, or your dad's? So you guys settle on each using your own values for your own cases. But wait, then if you took out your smartphones and tried to call each other, it wouldn't work because the electronics on each of your phones are different now, since you have different values of C. That's basically saying the physics when you're moving in a car are different than the physics when you're not in a car. And that's just weird. So which reference frame is the correct one? The dad's or yours? Or even more generally, which one is the right one in the whole world? So scientists decided that there must be one universal fixed reference frame called the ether. Two scientists, Michelson and Morley, set out to explore this idea. Using mirrors, they've shown light in two opposite directions, along Earth's rotation and away from Earth's rotation. With this concept of the ether, they expected that the light shown in this direction would travel at the speed of light, 186,000 miles per second. And the Earth is rotating counterclockwise here, so the light shown in the other direction is going in that direction, but it's also going backwards because the Earth is rotating. So it's going at the speed of light minus Earth's rotation speed. But this did not end up happening. Light traveled at the same speed in both directions. And this disproved the whole idea of having one correct reference frame. Light travels at the same speed in any frame of reference. But how can this make any sense? Imagine now, going back to our example, no matter how fast that car is moving, light is always moving away from it at the same speed. If it goes 50 miles per hour, 100 miles per hour, 1,000 miles per hour, or even 185,000 miles per second. No matter what, the light is still moving away from it at the same speed. Even more confusing, person B, who is not moving at all, also sees the light moving at that same speed. This is so insane, even sci-fi movies can't come up with this kind of twisted logic. It's just like saying that the speed of the baseball from you and your sister's perspective and from your dad's point of view are equal. But then Einstein came along, and he said maybe, just maybe, for those two sides of the equation to be equal, their times must be different. Actually, Einstein proposed that both time and space stretch or shrink to make sure that no matter how fast we move, the speed of light remains the same. Light is like the pacemaker of the universe. Just as your heart beats faster or slower to keep your oxygen levels the same when you're exercising or resting, so too does light regulate the beat of time to keep c constant. Isn't that just incredible? From this idea, it is actually quite easy to derive transformations that tell us how time changes from one reference frame, like your dad's, to another, like you and your sister's. If you want to see the derivations, watch my appendix video. The time in one reference frame moving with velocity v relative to another stationary reference frame is given by the following equation. Notice that when the velocity is 50, the velocity you and your sibling drove at in our example, v squared over c squared is practically 0, and so ta equals to. This is usually the case in everyday life, where cars and people don't go at a high enough speed for v squared over c squared to become significant. So we don't really notice a difference in time. Just like the baseball case. But when v becomes large enough that it's not negligible, the bottom half of the equation becomes smaller than 1, and ta is greater than to. And weirdest of all, if v2 is larger than the speed of light, you get the square root of a negative number, or imaginary time, which no one knows how to explain yet. And if you go at exactly the speed of light, you get 0 in the denominator, which equals infinity. Time stops. And as I mentioned before, length, or distance, also changes. This could be b, by the way, for bystander, stationary. These two results are called time dilation and length contraction. And they could have some pretty weird implications, like me leaving my little brother to go to outer space for an hour, and coming back to find out he's suddenly way older than me, because my time shrunk relative to his. So, by changing time and length, light shuts down our attempt at going near its speed by using reference frames, like a car and a bystander. But hey, here's another idea. What if we were to apply a force to something? Forces make objects accelerate, and their velocity goes up like this. So wouldn't the velocity keep on going up and up until it reaches the speed of light if we exert a force on this object for long enough? What's stopping it from reaching c? Well, what you're looking at is just the tip of the iceberg. Sure, the velocity goes up linearly like this with an acceleration, but it actually starts to taper off. It's asymptotic. Here, there is a literal mathematical limit at the v value of 186,000 miles per second. So the slope of that curve is decreasing, meaning the acceleration is decreasing. But if the acceleration is decreasing and we're applying a constant force, the mass must be increasing. This does not mean that the object is literally gaining more particles. Its mass is just going up because it's gaining more inertia. Now we have a problem. What about the law of conservation of energy? We are applying a force over a large distance, which results in a certain amount of work energy exerted. That work energy we expect to be translated into the kinetic energy of the object. However, as the acceleration slows down, the kinetic energy does not increase proportionally. So where does that extra energy from the force go? It turns out that the energy is actually transformed into mass. That is, mass and energy are interchangeable. And that's why the mass increases without there being more particles. With these ideas, Einstein derived his famous equation E equals mc squared. Using this equation, we can see that the energy stored in matter of a small cup of coffee is enough to power a small city for a year. So, if you can find a clean and safe way to convert matter into energy on demand, you will solve all the world's energy problems, climate change problems, world hunger, and probably many of the wars going on today.